it keeps happening. Not using if it's like a phone or if it's a tablet or a computer. But if if you convert for seconds or
I don't know if you can hear me, Ben, but I'm also having trouble. I'm going to do what you suggested right now. I'm getting off and logging back in.
exposed wire on this mic cord. That's good. That's good. Let's see. Are you hearing me now? All right, well, awkwardly enough, class is having a pause while we figure this out. Welcome back. Are you able to hear me now?
Yeah, I can hear you now.
Yeah, okay.
It was pausing a lot right now, but I'm good to go.
Huh. Okay, if there's any more persistent issues, guys, let me know. Cool, so it was just the microphone on this end, it seems. So, yeah, when in doubt, unplug it, plug it back in. Seems to solve everything. All right. Here's just another example. So if we were converting 700 or 7,920 yards to miles. In this particular case, like I said last time, you'll have like a sheet of how things fit together when you're taking the test. But in this case, we actually have something given where it says there are 1,760 yards in every mile. So based on that, you could do the same thing as on the last slide. You can say, oh, I have 7,290 yards, and you can multiply it by 1 mile over 1,760 yards. The yards unit cancels out. You end up with that fraction, and you just have to divide the numbers together, and you end up with 4.5. So the next couple of slides are largely here just as a refresher, and also so if we need to, we can refer back to them while we're doing the examples. But I have one slide on the American systems of measurement, so length being foot, inches, yard, mile, weight with pounds, ounces, and tons, and capacity with fluid ounces, cups, pints, quarts, and gallons. There's really no great way of teaching that. It's all just a memorize. Not my favorite. And same sort of thing with metric system, except in the case of the metric system, the useful things to remember are essentially what the prefixes mean and what the basic units are. So length has the basic unit of meter, mass has the basic unit of gram, Capacity has the basic unit of liter. And then you have all the prefixes going from the highest to the lowest: kilo, hecto, deca, deci, centi, and milli. And notice all the ones with the prefixes ending with an I are the small ones. So of course I made a bunch of examples, because why wouldn't I? But once we're past this short 8 problems, we can jump into percentages. I'm going to write out a few of these to start. All right. So we got some examples. The first one is 345 centimeters that we're trying to convert to meters. So all of these, every single one of them, you always start off with saying what you have right now. And for the purposes of our first problem here, I'm going to go ahead and put this over 1, just so you remember that when it comes to multiplying this by a fraction, this guy is going to end up multiplying into the top. It doesn't matter if you actually put the bar there and the 1. That's perfectly fine not to. But until you understand it and are able to do these no problem, that's a good way of making sure you'd make less mistakes. All right, so we're going from centimeters to meters. Now let's say for a second that I don't know what my unit conversion is, but I know I can go straight from centimeters to meters. Best thing to do normally, at least the way I do it, is I look at this and I say, okay, well, where are my units going to end up? Because that might be tricky to you at this point. You might not know if you do meters over centimeters or centimeters over meters. Well, what you end up wanting to do, you want to cancel out centimeters. And to make that cancel out, that means centimeters is going to have to be on the bottom over here, which leads meters to be on top. Once I have that set up, I can now say, oh, well, I got meters and centimeters. Which numbers fit in here? Well, I know that 1 meter is 100 centimeters. So I fill those guys in. And now I can see that the centimeters cancel out. And when I multiply straight across, 345 times 1 over 1 times 100. This is now in the units of M, so meters. And if I do that division, all that's really going to happen, kind of like when we're doing scientific notation, it just shifts over the decimal because I'm dividing by a bunch of tens. So I end up with 3.45 meters. Okay. Right. So now we're going to go from 5,674 meters to hectometers. And hectometers is one of the ones where it's a larger number. So in this case, hectometer means you have 100 of your original unit. So that means that hectometer is 100 meters. So I'm going to do this the same way I did the last one. Always draw my units out there. I'm not gonna do the fraction bar over 1 this time, but I am gonna kind of have it aligned to the top. That way I can see it a little better. And again, just like that last one, if I'm trying to get rid of meters, that meters is gonna have to be on the bottom over here. We're converting to hectometers. At this point, you can fill in what numbers need to go here. However many hectometers are in a meter, or vice versa, how many meters are in a hectometer? Well, 1 hectometer is 100 meters. Well, look at that. We have the exact same fraction happening as the first problem. Whereas in the case of centimeters being smaller than meters, hectometers happens to be bigger than meters, but because we're going essentially from a smaller unit to a larger unit, the same division ends up happening on this one. We end up making this number a little bit smaller by dividing it by 100. So we end up with 56.74 hectometers. Hope everyone likes having a lot of practice on these because I have a grand total of 8 of them. And I made number 8 messy. So even if you don't like writing these down, might be good to write down number 8 when we get there. So same sort of thing. We have 15 kilograms. And we're going to convert that to grams. Well, I know I can go straight from kilograms to grams. So again, that unit's going on the bottom, so I know it'll cancel out. Kilo means 1,000. So 1 kilogram is 1,000 grams. Kg cancels out. My units are now left with a G, so we're in grams. 15 times 1,000. Guess what that's going to be? 15,000 grams. This is when I noticed that that's cut off up there. I see. Okay. Okay. I'm just losing my mind. I'm here. I'm here. Okay. So now we have 15 kilograms to centigrams. Well, based on the units sheet that we have, or at least the slide that we have, we know that we can go from kilograms to grams, and then we can go from grams to centigrams. So we would have to do this one in 2 steps. Now, our first step's already taken care of because this guy right here, that's the last problem, right? That's number 3. So we already know that 15 kilograms to grams is 15,000 grams. From there, that's when we can actually go to centigrams. So we'll have grams down here and centigrams here. Centigrams is like centimeters, or honestly, just the word cents. That means it's 100th. So for every 1 gram, there's 100 centigrams. For every $1, there's 100 cents. So when you multiply these together, the grams cancel out. You end up with a 15 and a whole lot of zeros, right? 1, 2, 3, 4, 5 zeros. 15 and 5 zeros. Centigrams. So only 1.5 million. A little nicer to keep things in kilograms. All right, well, let's look at number 5. Number 5 is 2 kiloliters to decaliters. I don't remember what that is. 1 deca is 10. Okay, so in this case, a kiloliter is 1,000 liters, and 1 deciliter is 10 liters. Okay. If you don't know it off the top of your head, that's always fine, as long as you have something that you can actually refer to. Case in point, this is going to be one of the, other than the last class, first times I've ever used the unit deca. It's not something you use very often, if at all. All right. So we can do this by going from kiloliters to liters, and then we can go from liters to decaliters. KL to L. All right, so let's do that guy first. So I have 2 kiloliters. I'm going to go from kiloliters to liters. Makes sense. If 1 kiloliter is 1,000 liters, then 2 kiloliters is 2,000 liters. Kind of a pointless step, but you know, practice. Okay, so now we want to go from liters to decaliters. All right, well, we start off with what we ended here. We're at 2,000 liters. We're going to have to multiply it in such a way that liters is on the bottom and decaliters is on top. That way the liters will cancel, right? Well, we know that 1 deciliter is 10 liters. So that's exactly where you want those numbers. You want 10 on the L and 1 on the DAL. Okay. So when you multiply through, we end up with 2,000 over 10 deciliters, which is 200. Cool. All right. All right. Got a few more. Number 6, we have 2 cups to fluid ounces. This is my least favorite of the conversions. I can't just memorize what kilo is. I have to remember how many ounces are in a cup and what have you. Well, based on the slideshow, 1 cup is 8 fluid ounces. I probably made this problem a little too quick because I can convert it very easily. 2 cups, I'm going to multiply it by 1 cup on the bottom, 8 fluid ounces on top. Cups cancel, and I'm basically doubling what I started with here, really. So I end up with 16 fluid ounces. Two more. In this case, we have 1,600 ounces to tons. In this case, we know that 1 pound is 16 ounces. Right, 16. Yeah. And 1 ton is 2,000 pounds. So if we're starting with 1,600 ounces, it would make sense that we would have to go from ounces to pounds and then from pounds to tons. So that's what we're going to do. We want the ounces down here. We want the pounds up here. So I have 16 ounces, 1 pound. The ounces cancel. And we get 100 pounds. Now we can take that and convert it to tons. So 100 pounds. 1 ton is 2,000 pounds. Okay. Multiply through, we have 100 over 2,000 tons, which is effectively 1 out of 20, which should be 0.05, I believe. Yeah, 0.05 tons. Okay. Now those are the nice ones. I figured I'd do one problem that showed you guys where all this would essentially end up. And we're still skipping some steps on other things that would be useful. So in this one, I'm going to do it a little bit differently. This is going to be 3 miles per hour to yards per second. We haven't done anything like this yet. In fact, this is the only one we're going to do like this. So this one's particularly tricky because you have 2 units that you're converting. We're trying to go from miles to yards, and we're trying to go from hours to seconds. And if you remember last class, I showed you that we could, in fact, like take this last problem, we could actually go straight to tons if I had taken this guy right here, that second conversion unit, and multiplied it on here as well. Then we would have had 3 things to multiply through by, but it still would have worked out fine. That's essentially the concept you use on something like this. You would set it up as 3 miles per 1 hour. So you kind of look at it that way. And then the best way to do it, The best way to do it is that instead of doing it one step at a time, where we multiply it out and get a thing, and then we take that thing and multiply it through, the best way to do these is if we have all of our conversion units in a row. So let's say, for instance, hours. Hours is the easiest one to play with, right? Hours, we know we can go from hours to minutes and minutes to seconds. So what we're going to end up doing, we're going to have our conversion unit for going from hours to minutes right here. 1 hour, 60 minutes. And then the hours cancel out. But we're not going to stop there. We're not going to do our multiplication. We're not going to do that because right now our units are in miles per minute. Okay, but we're going to get there, right? We're going to multiply on another conversion unit. And we're going to go from our minutes to seconds. So to make minutes cancel out, if it's on the bottom, I have to put it on top. And I know that 1 minute is 60 seconds. So the minutes would cancel out. Well, what are our units now? We have miles over seconds. Okay. But we don't want miles. We want yards. What we can do is go from miles to feet and then feet to yards, right? We can do that. So we're going to actually end up multiplying that further onto this guy. I got miles on top, so miles is going to have to be on the bottom here. And then we're going to go to feet. Now I know 1 mile is 5,280 feet. So the miles would cancel. All right, well now our units are in feet over seconds. The units on top are feet, the units on bottom are in seconds, but we want to get to yards, so we're almost done. So we're going to multiply another fraction onto there. We're going to go from feet to yards. And 1 yard is 3 feet. At that point, our feet cancel. And you can look at your units now. What do we have? We have yards over seconds. What else do we have? A giant, horrible, jumbled mess, right? But that's okay. Because if you look at it, doesn't matter how many fractions you're multiplying by, it's always the top stuff multiplying together and the bottom stuff multiplying together. So before I even throw it at a calculator, I'm going to look at it as 3 times 5280 over 60 times 60 times 3. And that's in yards per second. So then we just figure out what this is. First, I'm going to multiply through on top and multiply through on bottom. 3 times 5280. Get a big number, but that's okay. It's just a number. Doesn't matter how many digits it's got. And we have 60 times 60 times 3 on the bottom. So we have 10,800. Okay. And again, that's in yards per second. Well, at this point, all you really need to worry about is dividing these. Throw it at a calculator. I'm just going to round it to the third decimal place. So I end up with 1.467. And that's in whatever units we still had, which is in yards per second. Isn't that fun? It makes a lot more sense when you do like 20 of them in a row, trust me. Most of this stuff comes to you by repetition. That's why I keep pushing everybody to do the whole essential ed thing. But there's like 4 of you who are. And 2 consistently. Okay. So that's all we got on unit conversions and unit measurements. Anybody have any questions at all over any of them? No, we're happy. Happy as can be. All right, so we're going to jump into percentages. So we're going to end up just kind of playing around with this stuff. It should be kind of familiar to most of you. But we're going to have some decent applications of them in here. So percent means parts per 100. Kind of like when we're doing the whole centimeters and centigrams and everything. Look at the word itself, percent, that means per 100. So based on this information, if you were to examine 25%, it could be thought of as 25 out of 100. Think of it as kind of like a fraction. So looking at 25%, we're going to start looking at converting percentages to and from decimals, which are very quick, very easy. So if you think about 25%, that's 25 out of 100. If you wrote that as a fraction, it'd be 25 over 100. And in order to find the decimal form of it, you just divide the top by the bottom. So 25 over 100 would be 0.25. Okay. And then if you were to convert it back, well, just think about what we just did. In order to convert it to a decimal, we divided it by 100. So if we were converting it from a decimal to a percentage, it would make sense that we did it the other way around. You can multiply by 100, and that essentially undoes that idea. So we end up with 100 times, I don't know what I got going on here. Oh, okay, I see what's happening. That's the last part of that sentence. You give it a little space there. I thought it was 100.0 point. Yeah, so you just multiply it by 100 to get 25%. So easiest way to do these, instead of actually doing the math of multiplying or dividing by 100, you can kind of see what's happening by doing that, right? It just kind of moving over the decimals. Same thing we did with scientific notation. Same thing we did when we were doing long division with decimals and we had to move things over. We can just use it as a shortcut. So if you're converting from percentage to decimal, you can drop the percentage symbol and move the decimal point twice to the left. So 25% becomes just a 25, which then becomes 0.25. And if you're converting it to a percentage, you kind of undo that. So you move the decimal point twice to the right and add the percentage. So you can kind of see that essentially all decimals are going to be between 0 and 1 for percentages. Because if you think about what we just did, if I had 100% and I converted it to a decimal, that would be 100 over 100. That just breaks down to a 1. So unless you're going into higher things than 100%, you're usually only going to be dealing with numbers between 0.01, which would be 1%, and 1, which would be 100%. All right. So let's look at converting from the percentages to fractions. So sometimes you have to actually turn them into fractions or vice versa. In order to convert any percentage to a fraction, you just put it over 100 and reduce. So that 25% we know is 25 out of 100. So you put 25 over 100 and then you try to reduce it as far as you can go. Well, 25 goes into the top, 25 goes into the bottom, and you'd end up with 1 over 4. I have as an example, 55% is 55 over 100, which breaks down because 5 goes into each of those, and you'd have 11 over 20. Now we have a bunch of examples. You sure love examples. Okay. We have 63%, and you're converting that to a decimal. Easy way to do it, find where your decimal is right now. Since this is an integer, you just have it right there. And then that decimal point will go to the left twice. That would do the same thing as dividing by 100, except it's a heck of a lot easier to do it that way, isn't it? So we'd have 0.63. You can see these are going to be kind of quick. Okay. Next one will be 45%. Now I'm going to write out a few of them real quick. So our second one is 45%, but we're not going to switch that to a decimal. We're actually going to switch it to a fraction. So with any percentage, if I was going to break this down into a fraction, a simplified fraction, I would put that over 100, and I would say, okay, what can I reduce this by? Because right now it's a fraction, but it's not as simple as it can go, right? So you'd say, okay, well, each of these is divisible by 5, right? So 5 could go into the top 9 times, and 5 could go into the bottom 20 times. So we would end up with 9 over 20. You would look at that and say, is there anything else I could break down by? No, not in this case, right? So 9 over 20 would be your equivalent fraction. Okay. All right, well, on number 3, we're back to converting to a percentage. So if we're converting this one to a percentage, we're just kind of going the other way as we did on number 1. Number 1, we were converting from a percentage to a decimal, so we moved that decimal over to the left. Well, in this case, we're going to a percentage, so we're going to move this guy to the right. Okay. That's going to give you 15%. I know on the slide I added an extra step where you were either adding or removing the percentage, but that doesn't really need to be in its own step. We can see what's happening when we move this over by 2. It's going to become a percentage. We can see what's going to happen on number 4. Number 4, if I'm converting this guy to a decimal, well, it doesn't matter that I have a decimal in my percentage. I just follow the same rule. This period is going to move over twice. I end up with 0.345. So it doesn't matter how complicated looking your percentage is, or your decimal for that matter. You always just do the whole move it over by 2 and make it a percentage or make it a decimal. In this case, number 5, we're going to make that a percentage. Okay. So that decimal right there is going to shift over by 2. We end up with 5.3%. You can absolutely, just like this last example, you can absolutely have a decimal in your percentage. If it goes past 2 digits, it's going to end up having a decimal. Okay. And then number 6, we have to convert 60% to a fraction. So again, you take that percent, change it to a basic fraction. We have 60 over 100. Let's be cheap about breaking this down. I like doing that. That's nice, it's convenient. It's a lot nicer to look at 6 over 10 than it is to look at 60 over 100. Okay, so I have 6 over 10. How can I break that down? Well, I know 2 goes into both of them, right? They're both even. So 2 goes into 6 3 times, and 2 goes into 10 5 times. Not bad. So these are pretty quick, right? Not too bad. Converting to and from fractions, decimals, percentages, it's not bad. You just move stuff over or make it a fraction, break it down a little bit. It's doable. Moving on, so we got more stuff with percentages. So now we can actually go to actually using these for something, now that we know how to convert stuff around. So using basic math, we can use percentages to give us exact values when comparing to a number. So for example, what's 50% of 12? Well, in this particular case, you're probably able to just look at that and say, oh, well, 50% means half, and half of 12 would be 6. But not every problem is that simple. So having a good method of converting around is very nice to have. So in order to find this answer, you can take that 50% and convert it to a decimal. So you'd have either 0.50 or 0.5. That 0 on the end of the 0.50 doesn't much matter. So you can look at it either way. And if you want to find the percentage of something, all you gotta do is multiply. So to find 50% of 12, you can take that 0.5 and multiply it onto the 12. So you end up with a 6 there. And if you look at how that worked out, you end up seeing that if you take your percentage piece and you multiply it by the whole part of the number you're looking at, you set that, that is always going to equal whatever part it is that you're looking for. So the percentage part. So we had the percentage 50% multiplied onto our whole 12, and we ended up with just part of it, 6. So we can see that 50% of that 12 is 6. So that particular setup is something that I keep referencing throughout the notes tonight. So that's a bit of a simple example, but let's look at a more tricky one. Let's say you're putting something to a vote and you need a simple majority, which would be 51%, in order for the vote to succeed. Now, if there are 6,032 voters, let's say you wanted to find the amount of votes needed for it to succeed. So first, you would convert that 51% to a decimal, which would be 0.51. And you take that decimal point and you multiply it onto however many voters you have, because that will show you how much 51% of your voting population is. So you have 0.51 times the 6032. And I kept a couple of digits in there when I did the multiplication, but ends up being around 3,076.32. Now, normally you would be done and you'd be like, yay, there's my number. But you know that that's the point where we need to be higher than that number in order to succeed, right? Like that's the exact amount of 51%. But we can't have 1/3 of a person. So on particular word problems like this, you would know that even though it's smaller than 0.5, we would want to round up in order to account for that 0.68 missing vote that we would have. So you would end up with saying that your amount of votes needed to succeed was 3,077. So you'd go up 1 just to account for that difference. So I only have a couple of examples on these ones because they all work out roughly the same. Now, our first one, I'm going to kind of break that guy down over there. Our first one's just asking for 8% of 5650. Our second one is asking for 76% of 817. And then the third one is saying if you need at least a 3/5 majority, to succeed in a vote of 5,600 people, what's the lowest amount of votes needed to win? All right. So 8% of 5,650. It's actually not too bad. It's actually not too bad. Because we're just going to take that 8%. We're going to convert it to a decimal. So that decimal is going to move over twice. We end up with 0.08. And if we're trying to find that of 5,650, you end up multiplying it by 5,650. That is it. That is all you have to do. Throw it at Mr. Calculator and I get 452. Okay. Same thing happens on number 2. I have 76% of 817. Well, 76%. That's going to be 0.76. And we're going to multiply that by the 817. All right. End up with a bit of a funky number, but that's okay. I ended up with 620.92. Sometimes you don't really get the nicest numbers. Now, if you were doing this problem where it was saying 76% of this many people, just in general, not in terms of like a vote or anything, you would round to the, essentially usually to the nearest. So it'd be 621. With word problems, it gets weird as to whether or not you round up or round down. It just depends on the context. Like if you're looking for a majority of votes, you can't have a partial vote, so you have to round up. If you're playing with populations and you're guessing a population, you're saying how many people are going to be there at the end of this amount of time, and you end up with like 42.2. You can't have 0.2 of a person, so you'd round down. Even if it was 0.7, you can't have 70% of a person, so you round down. It's just essentially how it makes sense. So if you're looking for a 3/5 majority of 5,600, you can do this a couple of different ways. You can take this fraction and convert it to a percentage. We didn't really play around with converting to a percentage, but the basic idea would be that you would find whatever gave you a denominator of 100. So say this 5 here, I would have to multiply that by 20. So I'd multiply the whole thing by 20 over 20. I would end up with 60 over 100, which would be 60% or 0.60. I can look at it that way. And then I would take that and multiply it by the 5,600. But this one's kind of a trick question because we don't even need to play with percentages. We can. I mean, if you ever run into this situation on a homework and you're like, oh, I could solve this other way. Yeah, but they're kind of trying to teach you the percentages. This would be one way to do it. And for the purposes of this homework, essentially, of this class, that's how we would prefer to do it tonight. However, all we did was find an equivalent fraction or equivalent percentage for a fraction. 3 divided by 5 ends up being this 0.60 or 0.6. So on this particular problem, you can just jump straight into the multiplication and do it that way. If you're finding that percentage of something, you can also just find that fraction of something. Either way, you end up with the same answer on this one. Either way. Now, what do I get? Is it 3360? 0.6 times 5,600, 3360. And my carpal tunnel's giving me trouble. Cool. Love having a desk job where I type all day. So either way you do that one, it works out. Okay. All right, we only have 10 more slides. That's pretty good if we've gone through 16 since the start of this. Pretty good. We're probably gonna have an early night. If any of you are sad about that, we can do more work. Okay. So we can take what we've just learned and apply it to some different scenarios. In the last examples, we took percentage of a whole to find a part. Every single one of those, right? We took a percentage of something, and we found a smaller something. So if you look at that, and this is actually a very useful thing, this applies to every single algebraic concept you will ever look at in your entire life. You have 3 pieces of information, one of which you don't know, and you know the other 2. You can take those 2 and find that 3rd piece that you don't know. Every single time, every formula you ever use, you need 1 less than however many variables you have. Every single one of them. So in the case of percentage times whole equals part, if I have 2 of those, any 2, I can find the 3rd. So if I look at that a little bit more analytically, you have percentage times the whole is equal to part. Well, that's multiplication. And based on multiplication, if you want to undo that, you could actually divide both sides by either of those words, either of those terms, right? So those are just, they're not different formulas, but they're different ways of representing the same formula. So if you divided the left side, well, both sides by the percentage, you would get whole is equal to part divided by percentage. If you divided both sides by the word whole, the term whole, you would have your percentage is equal to the part out of the whole, which makes sense. That one makes a lot of sense. Both of those come up fairly regularly, particularly the last one. But as long as you understand what it is you're doing, usually just kind of trip your way through it. It's not too bad. So let's look at the first of those 2 examples. Let's say that you don't know what your whole number is. Say you have the percentage of some amount that leaves us with only part of that larger number. In this case, we have the knowledge that 7% of some number is 56. So let's look at this basic setup. And in fact, for the most part, instead of cleaning up the, like playing around with the formulas like I did on the last slide, I'll usually just keep it as percentage times whole equals part. That way it's a little bit easier to understand and you can apply that concept to all of them. Also, I did not want to play around with the formatting of this, this slide. So you can see I kind of did all my steps side by side. Not my favorite way of doing things. So in this case, you can put those pieces together that you know and substitute the larger number with a variable, and then you can solve for that unknown number. So we know we have 7%. We know that the 7% of whatever that is 56. So we can set it up like that first guy right there. 7% times W, I use W for the word whole. Doesn't really matter. I could put an X, I can put a picture of an apple. Doesn't matter. It's a variable. It's a thing I don't know. So 7% of thing is equal to 56. All right. So you clean it up a little bit. You convert that 7% to a decimal. We end up with 0.07W is equal to 56. Well, from there, if we were going to solve for that W, we would have to divide both sides by that 0.07, right? Undo that division. So we divide both sides by that. We get 56 over 0.07, which cleans up to be 800. So that means that 7% of 800 is that 56 that we started with. Okay, so we've done it two different ways. We've been able to find that part. We've been able to find the whole, but what if we need to find the percentage? What if you don't know the percentage? So if you have, say, 36 out of 450, what's the percentage of that? What do you have? Well, if you go back to that formula, you have percentage times 450 is equal to 36. And you can see from that, I just took the letter P for percentage as my variable. I said, okay, I have 450P is equal to 36. I can divide both sides by 450. I get 36 over that. And then I would throw it at a calculator. We happen to end up with 0.08. Converting that to a percentage, we have 8%. Okay. Yeah. So it's a very useful concept, but even if you forget any specific method, if you remember the basic formula, plug in what you know, and solve for what you don't know, you're going to be in good shape. So percentage times whole equals part. Okay, you got two of them, you can find the third. So let's look at a couple of examples. Oh yeah, this is going to be a much shorter class tonight. I apologize. I do not have 2.5 hours of math prepared. The next unit is nothing but graphs and bar graphs and circle graphs, not graphs, and yeah. So I was planning on my weekend drawing those out for the slideshows. So what is the percentage if we have 43 out of 345? Okay. Well, percentage times whole is equal to part. We know both of these pieces, so we can easily find this one. Probably leaving it as a symbol is not a good idea, so we can call it a variable, doesn't matter what. I'll just call it an X, I don't care. We know that our whole amount is 345 and our part amount is 43. Not much point in rewriting this as 345x. We can see the multiplication happening now. So we can just divide it off. That'll give us x is equal to 43 over 345. That's where the calculator comes in. Thank you, calculator. It doesn't care. It just spit out the same percent fraction. Okay. So it gets something confusing and long and hideous, right? So I'm going to take that to a couple of decimals. Yeah, I'm just going to take that many. Why not? And then we have to make sure, because this is the decimal form of a percentage, we have to make sure that we convert it to a decimal or to a percentage. So we are going to have to move that over to, we get 12 point, whatever you put here, we're definitely going to round a little further than that. Let's just call it 12.5%. So 43 is 12.5% of 345. It's not too bad. I could have very well called it 12.46 if I wanted to, or 12.464. Or something giant and horrible. Doesn't much matter. Okay. So the second one says, if we know that 24% of a number is 402, what is the number? So 24% of some number is 402. What is that number? Well, same thing comes into play. Percentage of the whole is equal to the part. So we have 24% of something is 402. So I can convert this guy to a decimal. Just moves over twice, right? So it'd be 0.24. Normally you want to put a 0 in front. Something I'm very guilty of not doing every time. So 24% of something. Well, that would be the same as multiplying, right? We're going to end up multiplying, same as our formula up here. So the question is, what do we call it? Doesn't matter. I could have an S, I could have an X, I could have, I don't know. Let's do a V. Nobody does V, right? It's a V. Whatever. As long as you don't do a lowercase l, so it's just a line that looks like a 1, then you're good. Okay. Then to solve for that variable, you would divide this off. So V is equal to whatever that is. 402, 402 divided by 0.24. We end up with 1675. Which makes sense, right? 24% of something is 400. That's about a quarter. So we know that this thing's probably going to be around 4 times that. 4 times 400 is 1600. That's a decent estimate. Gets us there. Okay. The next one is saying what percent of 850 is 78, and round to 3 decimal places. And that's a pretty common way you'll see things written when you're in classes or on tests or something. if you know you're gonna end up with a weird number, if they say round to the nearest whatever, not round to 3 digits, usually that means that it's going to be some weird number that kind of goes on forever. So same thing. What percentage, let's use the letter P, of 850 is 78? Okay. We can divide that off just like we did earlier. So we have 78 over 850. I get 0.091765. And notice I'm not rounding yet, because this one says round to the 3 decimal places. I'm not going to round right here because I haven't converted this to a percentage yet. If I converted it to a percentage first and then rounded to 3 decimal places, my answer will have 3 decimal places in it. If I converted it, or if I rounded right now, and then I converted it to a decimal or a percentage, I would only have 1 decimal place. So generally, you want to get to the point where you're done before you round. Rounding should be your absolute last thing you're doing if you're giving a rounded answer. So this guy shifts over twice. And I'd have 9 points. At this point, 1, 2, 3, this is the decimal point place I'd want to round to. So I look at the digit after it and I say, okay, well, the digit after it is 5, which means this one's going to round up. So I'd end up with 177. That's after we converted it to a percentage. So 9.177%. And if I punched it into my calculator just to be sure, if I took that 0.09177, multiplied it by 850, well, I end up with something with a bit of a rounding error, 78.0045. So you know we're pretty good when we have very, very tiny rounding error. Okay. Any questions, comments, concerns on any percentage stuff so far? Okay. So we have a couple of concepts left. We have percentage increase and percentage decrease. And then we have some discounts. And then once we get those ideas, then we're pretty much golden on percentages. I'm very disappointed that it took me a few hours to write this and then cutting through it like a madman. So say you're once making about $12.28 an hour, and you're now making $13.75 an hour. How would you find the percentage of the raise you got? I mean, let's face it. Tons of employers will be like, oh yeah, you got your annual raise. And then they just wouldn't tell you what's happening from there. And you're like, you'll look at your paycheck, you'll figure it out. Now, granted, if I got more than $1 a raise every year, I'd be happy, but you know. So in order to find out what the difference is, you find the percentage of the initial amount this actually ended up being. And you use that same concept as before, where the percentage times the whole would equal the part. If we had solved that for percentages, or for the percentage, we would have that the part over the whole would equal the percentage, right? I'm going to make a little note on that. So we're kind of using one of the shortcut methods from one of the earlier slides. So you figure out what the difference was. So between $12.28 an hour and $13.75 an hour, the difference is $1.47. And then you have to figure out what that what percentage that $1.47 is of what you were making. And all of these, you always find the percentage of the initial amount you started with, because you don't much care. You're not treating that $13.75 as your starting point. You're treating that as your ending point. You always are looking for the percentage of your original amount, which is $12.28. So we put the $1.47 over the $12.28, do the division, and we end up with 0.119707. And I said we could just go ahead and round that to 12%. We don't need to call it 11.9707, because at this point you're within very minuscule parts of a dollar. We're not really playing with anything at that point. So anything past that would just be a rounding error. So that means you got a 12% raise. So the same concept applies on a percentage decrease. So let's say that you randomly found a ridiculous amount of oil that caused the crude oil prices to plummet, leading to a decrease in the cost of gasoline. Say our usual spot has gone from 3.499 per gallon, and I put in the third digit because, hey, everything always says 9/10 of a penny at the end of it. Guess what that's rounding up to? Another penny. Nobody pays attention to that, but hey, whatever. So we have 3.499 per gallon, and it's gone down to 2.149 per gallon. So you're asking for what the percentage decrease would be. So again, you find what the difference is. So you would subtract them. You end up with $1.35 in this case. And then just like that last one, you want to divide by the original amount. So you went from 3.499. So that's what you're going to end up dividing with. So you have the 1.35, and you're dividing it by 3.499. You end up with this long string of decimals. 0.385, 825, blah, 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 blah. You don't quite need it nearly that far. So you convert it to a decimal. Depending on the question, you can round it pretty nicely. I rounded it to the first decimal point after that. So it ends up being a 38.6% decrease, which would be nice. Okay. And those concepts can be applied to a lot of different things. So, for example, you're in a store and you're grabbing a piece of clothing that's normally $14.99, but it says 15% off. So what is it? Well, not bad. What you're going to do is you're going to find 15% of that $14.99. Again, percentage times whole is equal to part. So 0.15 times the $14.99 is equal to $2.25. So we found out that the amount that's coming off of it is $2.25. So to figure out what the current price is, you do the original amount minus that $2.25. There's a couple of ways to do this. I just went with this way because it'd be a little easier to teach it. But another way to do this is if you look at this and say, oh, well, it's 15% off. What is it now? You could say, oh, well, what do I have left as a percentage? Well, if I took 15% off of something, that means I have 85% left. So you can very well just take the 0.85 times the $14.99. And you would punch it in a calculator, you would actually get that 1274 right away. So you could do that. Now, when you're learning discounts, usually they're asked of you in a couple of different steps. They'll often ask you what the discount amount is first, and then it'll ask you what the final price is. So that's one reason why I decided to go with this method, because that'll always give you those two answers, those two concepts. All right, so I'm sorry to say that this is the last slide of my class tonight. So you're gonna end up being free of me much earlier than usual. But you know, somehow I feel like everybody's going to survive. Okay, so we have a bunch of random percentage examples. Our first one, the temperature outside is going from 57% in the afternoon to 17% at night. We want to know the decrease. I like that I put percentage. This is clearly supposed to be a degree symbol. Oh, tired Ben was at it again. Tired Ben was at it again. I'm gonna write down a few of these while I go. My second one, if you order 20 chicken nuggets and you get one extra, the most special of nuggets. What is the percentage increase? Which is essentially asking, hey, what percentage did we just pull off from that? So I'll write those first two down first. So we have 57 degrees and we're going to 17 degrees. And we want to know what the percentage decrease is. So what you end up doing is you find the difference first. So find diff. So 57 minus 17, we would end up with 40 degrees. Obviously enough, right? We've gone down 40 degrees. Now you divide that, because that's the amount that you've changed, right? You divide the amount that you're changing by over whatever it was you started with. In this case, it was 57 degrees. And you'll end up finding the decimal form of your percentage. So I end up with 40 divided by 57. Got this big ugly thing. 0.70175, good enough. And I can convert that to a percentage by moving over twice. And I get 70.175%. That's a heck of a decrease. Nevada nights are weird. That's pretty much where I was going with that. We lose 2/3 of our heat at night. It's horrible. Okay. Then we got a 20 piece. So we had 20 nugs. We got one nug. I'm going with nug. I have no regrets. We want to know what the percentage increase is. Okay. So you wouldn't want to look at it just as this. We could actually jump straight to finding what the percentage increase is, but I do want to show you that depending on the problem, it might be good to be able to recognize that you're going from 20 to 21. And in this case, the difference is that one nugget. Either way, you take your difference, which in this case would just be 1, right? Divide it by what you started with. And you should end up with 0.05, 0.05, right? Yeah. Which is a 5% increase. You have received a 5% increase in nugget. Isn't that exciting? Talk about firefighters and policemen. No, the people who work fast food that give you 1 extra nugget, those are the real heroes. Yes, I am completely aware that I am ridiculous and sarcastic. I don't actually believe that, as a disclaimer.
Did you say this was the last slide?
What was that?
Did you say that this was the last slide?
Yep.
Okay. Unfortunately, I have to get off a little early as well because I have to take my kids back.
That seems like a good reason. You're good.
All right. Thanks, Ben. See you next week.
Have a good night.
All right, you too. Bye.
Okay. Well, he's missing my favorite problem because, of course, I always have to be ridiculous with at least one problem. You find yourself with a 20% off coupon for a Turbo Man figure, the very same from the 1996 Christmas classic movie, Jingle All the Way. The store has its price listed at $29.99. What is its current price? Okay. So we have $29.99 and it's going to be 20% off. So we need to figure out what 20% of $29.99 is. So percentage times the whole. We convert that to a decimal, it'd be 0.20, right? Multiply that onto your original amount. And we get 5.998. I'm pretty sure we can round that, right? I mean, we're talking about dollar amounts. If we're talking about dollar amounts, you would normally round that to the second digit, right? Well, that's going to round this up, which will round this up, which will round this up. $6. That's about 20% of $29.99. So we figure out what our original amount is, because that's just the discount amount, right? I'm going to write that next to it. Discount amount. That's just our discount amount. We need to find our actual total, which is $29.99 minus that discount. So we get $23.99. That right there would be how much it costs being 20% off. Now, number 4 has us referencing number 3. What is the total after the 7.6% sales tax? So we're assuming this is sold in Carson City. Okay. So we know that sales tax is coming off of what you're starting with. Now, in this case, we're not going to be looking at that $29.99, right? You would take the discount amount first, and then that's what you're going to take the percentage of. That's your subtotal. What's the total? So we figure out what the tax amount is. We take that 7.6%, convert it to a decimal. So it moves over to the left twice. You end up with 0.076, right? Because remember, we're doing that. And we multiply that by the $23.99 that we got in the previous problem. All right. So I get 1.82324, blah, 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 blah. It goes on forever, right? I actually think it just ends there, but whatever, whatever. Remember, this is a dollar amount. So we're gonna round this to the nearest penny. Okay, so we're gonna take this, we're gonna add it to our subtotal. So we get $23.99. This is gonna be our actual total. Add the $1.82. We end up with $25.81. That is how much this guy would be after a 20% discount and then 7.6% sales tax. Netting you a little over 10% off because sales tax. Cool. Anybody have any questions on anything? Or are you all okay with being 45 minutes earlier out today? Yeah, I think you're happy. You're like ready to run. Also, I love the backpack. I see the Avengers.
Thanks.
I am a nerd. All right. Well, sorry about the shorter class tonight, guys.
No, it's okay, Peter, thank you so much.
Yeah, you were very happy about it.
Because I have to drive today.
Oh, God, okay. All right.
I'm worried. In the morning.
All right, everybody. Well, I hope you have a good night. If you have any more questions, feel free to email me.
And it's Friday.